Hello, everyone, and welcome to the TIFR Colloquium. I would like to introduce Hyunju Kwon from ETH-Zurich, who will tell us about Euler flows and strong Onsager conjecture. Over to you.
Thank you very much for the invitation to the colloquium at TIFR. So as you see in the title today, I'm going to talk about some fluid equation called Euler equation and strong Onsager conjecture imposed on it. So let me start with the equation. So this Euler equation describes the motion of incompressible inviscid fluid. And here incompressible means that the density of the fluid remains constant in space-time. And inviscid means that the fluid has no viscosity. So in other words, we're gonna ignore the friction force. So very roughly speaking, this is not rigorously true, but you can just imagine a flow of water. So you can consider the equation describes the motion of water. Okay, so here is the system. And as you see, there are unknown functions, u and p, where u is a vector valued function, which represents the velocity of the fluid, and p is a scalar function, which is pressure. So if you write the first equation component wisely, it will be actually 3 equations. And just to help your understanding, if I write down the first component equation, it will look like this. So here the operator u dot grad means that the following, as you may guess. And this operator applies to u1 component and partial 1p. And there are 3 equations. All right, so these systems are derived from a simple physics law. So first, the divergence-free condition can be derived from the mass conservation. So here, mass conservation means that when you take some arbitrary region on a domain, on a spatial domain, and it says that the rate of change of mass in this region will be balanced with the net mass flux through the boundary. So if I write it as in terms of equation, then it means that the rate of change of mass, so here rho denotes the density, will be balanced with the flux on the boundary. And here n denotes the outward unit normal vector, then I think I need a minus sign. Okay, and then if you apply the divergence-free condition on the right-hand side, you will get the following equation. So, and since omega is some arbitrary region on a domain, this will lead to the equation for the mass conservation. And recall that we assume that fluid is incompressible, meaning that the density is constant. So this from mass conservation and incompressibility assumption, we have divergence-free condition. Okay. And in a similar way, you can also derive the first equation using momentum conservation, or you can see the first equation as Newton's second law of motion in Lagrangian coordinate. So if you look at it, the left-hand side terms describes the acceleration of a fluid particle, and that will be balanced with the force acting on the particle. And under our, in our setting, the only force is generated by difference in pressure. In particular, for example, water flows from the area of high pressure to the area of low pressure in a direction of minus gradient P. You will have some force. So this is the system, and today I will talk about this system. I will mainly talk about this system. But before that, let me also introduce the Navier-Stokes equation, which you may heard about it if you are from the Millennium Problems. So if you look at the equation, it's almost same with the Euler equations, but it has the additional term. which describes the friction. Indeed, the real world fluid has all viscosity, so it actually has friction. So in account of such friction force, the Navier-Stokes equation was introduced. And if you look at this dissipation term, in front of Laplacian, there is a positive constant called viscosity. And this constant measures how sticky the fluid is. So for example, water, let's see, the viscosity of water will be smaller than the viscosity of, for example, honey, because honey is much sticky. Then you may ask, well, apparently Navier-Stokes equation better describes the real world fluid than the Euler equation. Then why do you study Euler equation? There are many regions, but one of the important regions is related to the turbulence, which you may feel in the airplane. So according to the famous physicist Richard Feynman, he says that the turbulence is the most important unsolved problem of classical physics. So both physicists and mathematicians, we want to understand the turbulence in a better way. And to this end, we are particularly interested in small viscosity flows, because these flows tend to be more turbulent at the same lengths and velocity scales. So to see this, you can imagine the following situation. So we have two same size of cup, and so the length scales are same, and we put water and honey to each of the cup, and then stir it rapidly with the same speed. So the velocity scale is same. And then you can easily imagine that honey, which has a greater viscosity, will show more stable phenomena, while water, which has a smaller viscosity, show more relatively chaotic behavior. So you can see that the small viscosity flow show more turbulent behavior. And in our interest in this very small viscosity flows leads to the interest in the extreme case when nu equal to 0. So this is one of the reasons that we want to understand the behavior of this solution behavior of the Euler equation. And in this talk, I will particularly pay attention to the dynamics of its kinetic energy. Okay, so first let me start with a total kinetic energy conservation, which is pretty much a classical result. And it says the following: if we consider a differentiable solution in space-time to the Euler equation, the total kinetic energy, so here total means that we sum all the kinetic energy in this whole spatial domain. But before that, okay, so from now on, let's restrict our domain, the spatial domain, as the periodic domain. Okay, so in such case, the total kinetic energy is defined as a 1/2 of the square integral of velocity on a whole the periodic box, and this quantity doesn't change in time. So in other words, it is conserved. Okay, so the justification of this equation is pretty easy. So first, we recall the momentum equation, which looks like this. And then we inner product velocity to the equation. And then by using product rule, this is the equation that we're gonna get. And using the divergence-free condition of velocity, the second term can be written as a divergence form. And if you look at this equation, it already describes the dynamics of kinetic energy. And this equation is also called local energy equation, equality. So what it says the following: if you look at the equivalent form, then equivalently it says that for any local region in a periodic torus, the rate of change of kinetic energy on that region will be balanced with the energy flux through the boundary. So in other words, it means that every local region, the kinetic energy is conserved. Then of course, the total kinetic energy will be conserved. But just to see this, you just plug the periodic box into omega, then the second term will disappear because of the boundary, periodic boundary condition. Okay, so in this way, we have the total kinetic energy conservation for differentiable solution. And the question is the following: for irregular solution, does the conservation persist? So here, for the irregular solution, you can just think for example, non-differentiable solution, the solution whose value is changing pretty widely. So for such solution, I mean, we are interested in such solution because in general, turbulent flow doesn't have a good differentiability. So such solution, we are wondering the conservation still holds. Indeed, if you look at this total energy conservation, the total kinetic energy is well defined as long as the velocity is square integral. Okay. But if you think naively, well, since the equation doesn't contain any external force, then shouldn't the total kinetic energy conserved even though solution is irregular? But surprisingly, physicists found a negative evidence for this question. Indeed, they observed anomalous dissipation of turbulent flows. And such observation is like formulated as a Kolmogorov-Zero laws in the following way. So it says the following: in a vanishing viscosity limit, the ensemble average of the dissipation rate of total kinetic energy remains positive. So let's go a bit slowly. As I mentioned, the real world fluid has all positive viscosity. So to measure some property of the Euler, the solution to the Euler equation, what you can do is using the vanishing viscosity. So, and then if you measure the dissipation rate of kinetic energy of viscosity flow, so for example, if you consider smooth Navier-Stokes flows, then by repeating the same computation that we just did, we get the following equation. So previously, the right-hand side was 0 in the case of Euler equation. So when nu equal to 0, we obtain 0. But if you look at the Navier-Stokes equation, we have the additional term which describes the friction, and from this term we obtain the this new term on the right-hand side. And this term in general has positive value, so you can see that the friction leads to the total kinetic energy dissipation in time. And moreover, the friction is the only source of the dissipation. But surprisingly, if you send viscosity to 0, the limit doesn't converge to 0, rather it remains strictly positive. So this means that in the vanishing viscosity limit, there's a still remaining dissipation. Then you may ask, what's the source of such anomalous dissipation? To this question, in 1940s, physicist Lars Onsager answered that the lack of smoothness of solution can be the source of the dissipation. And he even quantified the regularity of solution and proposed some critical space for the total kinetic energy conservation, which was called Onsager's conjecture among mathematicians.
I have one question. Sorry for interrupting. So what is this ensemble with respect to this expected value? So in the previous page.
Sorry. Okay. Yes.
So after limb soup, you have this bracket, right? What is
Yes.
that?
So it's a sort of ensemble average, but this is what physicists do. So like they assume that there's some nice invariant measure that we can take the average.
I
So,
see.
but I don't think mathematically it's proved that there exists such invariant measure, at least for 3D in Navier-Stokes, as far as I know.
I see.
Yeah.
Okay. So
Yeah,
it will be
thank
some
you.
kind of field theory stuff.
Sorry?
So it will be some kind of field theory associated with that.
Yeah.
Yeah.
Yes.
Okay. I get that. Okay. Yeah. Okay.
Yeah.
Thank you.
Thank you. Yes. So yes, but so it was called Onsager conjecture among mathematicians, but in a recent resolution of the conjecture by Isett, we now call it as Onsager theorem. So here is the statement. If a weak solution to the Euler equation is alpha Hölder continuous, so here weak solution, you can think it as some generalized version of a solution, because now we're gonna consider a solution which is not even differentiable. Okay, and its alpha Hölder continuous means that it satisfies the following inequality, where C is some constant independent of time. And you can roughly think the alpha Hölder continuity as so here alpha will be some number between 0 and 1. So you can consider it as like fractional number differentiability. Okay, so using this alpha Hölder continuity, Onsager quantified the regularity. And he says that when alpha is greater than 1/3, the total kinetic energy is always conserved, while alpha is less than 1/3, the conservation may fail. But on the other hand, when alpha is equal to 1/3, whether the total kinetic energy is conserved or not, it still remains open problem. Okay, so now let me revisit the history behind this theorem. So the conservative part was actually proved in early 90s by Konstantin E and TT. And after that, Duchon and Robert proved that if Euler flow is alpha Hölder continuous for alpha greater than 1/3, it not only satisfies total kinetic energy conservation, but in fact, the kinetic energy is conserved in every local region. So in other words, it satisfies the local energy equality. Okay. On the other hand, if you look at the non-conservative part, so here what we want to do is the following. When Euler flow is alpha Hölder continuous for alpha less than 1/3, the non-conservative solution we want to construct the non-conservative solutions. So in this direction, in early 90s, Schaeffer and Shirama constructed some L2 integrable non-conservative weak solutions. So Schaeffer started the work on R2 domain, and Shirama extends Schaeffer's work on a periodic domain when n is equal to 2 and 3. And after that, Lellis and Cyclidi constructed non-conservative bounded weak solution on n-dimensional periodic domain for n greater than or equal to 2. But more importantly, they sort of suggest a systematic way of constructing solution by introducing convex integration scheme to the Euler equations. And such scheme has been used actively even nowadays to other fluid models. Okay, but this scheme didn't work very well when they tried to construct a whole non-conservative Hölder continuous solution. So they instead adopted Nash's idea and constructed non-conservative Hölder continuous solution when alpha is less than 1/10. And the range of alpha has been improved up to 1/5 by Buckmaster, Lellis, Isett, and Cyclidi. And eventually we reach it 1/3 by Isett. So if you look at the Isett theorem, the statement is the following: for any alpha less than 1/3, one can construct a non-trivial solution in C alpha space with compact support in time. So if you draw the graph of the energy profile, meaning that the graph of the total kinetic energy, such energy profile will be also compactly supported. So for example, it will look like this. So obviously it is not conserved. So you can see that the constructed solution doesn't conserve the energy. And the solution, which looks like this, also called a nightmare solution, because if you think about the possible scenario to have such an energy profile, you can imagine the following. So you put some water next to your bed, then the water will initially just remain stable. So the velocity of water will be 0, but while you're in a dream, the water suddenly start to move by itself. So it start to have energy. And then when you wake up, the water again goes back to cup, and then it remains constant. But of course, this kind of nightmare solution cannot exist in the real world. And indeed, the main reason is in the real world, we don't allow the creation of a total kinetic energy. So to resolve this issue, Buckmaster, Lellis, Cyclohidi, and Bicol proved that for any alpha less than 1/3, we can actually construct a wholly continuous solution which has a prescribed energy profile. So it means that we can construct a solution which has the energy, which has the total kinetic energy that we want, the energy profile that we want. And of course, we'll be particularly interested in non-increasing energy profile, because the solution which has such energy profile have some chance to be physically meaningful. So so far we talked about the Onsager's theorem and related results. And now let me move on to the one of the main questions in this talk. So the question is, are the constructed non-conservative solution for the Onsager conjecture actually physically acceptable? So to answer this question, we first need to talk about what is physically acceptable Euler flows. In fact, we haven't had an agreed definition of physically acceptable Euler flows, but such flows are expected to be recovered as a vanishing viscosity limit of physically acceptable Navier-Stokes flows, because as I mentioned, the real world fluid has all viscosity. And among all knowns, one of the most physically relevant solution class to the Navier-Stokes equation is the class of suitable weak solution. Then the question is reduced to the following. Can we write the constructed non-conservative solution as a vanishing viscosity limit of suitable weak solution to the Navier-Stokes equation in some suitable topology? So first, let me recall the definition of suitable weak solutions. Since it's a weak solution, it satisfies the equation in some sense, so in a distribution sense, and it is in the following energy space. So this is sort of a minimal requirement to discuss the rate of change of the kinetic energy of the Navier-Stokes equation. And the last condition is the local energy inequality, which looks like this. And the physical meaning of the local energy inequality is the following. So as Onsager said, the irregularity of the solution, it can give the either creation or dissipation of kinetic energy. But this inequality doesn't allow the creation of kinetic energy originate from this irregularity, because such things are non-physical. So that's the meaning of the local energy inequality. And the important property of this suitable weak solution is that this solution only allows a singular point, the singular set, to be a one-dimensional Hausdorff measure zero, which means that when you collect the point which whose value is like essentially not bounded, the size of such set can't exceed the even line. So it's pretty small set of singularity. And for that reason, we consider suitable weak solution is as one of the most physically relevant solutions. So going back to our question, so the question was, can we write the constructed non-conservative solution as a vanishing viscosity limit of pseudo-weak solution to the Navier-Stokes equation? Answering to this question seems to be pretty challenging with what we have so far. So instead, we have some progress in this relaxed version of relaxed problems. So let me introduce these relaxed problems. So one possible direction is the following. Instead of considering a pseudo-weak solution, you can consider much weaker notion of the solution. So if you look at the Buckmaster and Vico's recent work, this theorem states the following. Let's say we have a weak solution to the Euler equation in C alpha space for alpha greater than 0. Then we can always find a sequence of very weak solutions such that the sequence are uniformly bounded in L infinity in time and Sobolev space in space for some beta, pretty small number. And such sequence will converge to the given Euler flow in L infinity in time and L2 in space in the vanishing viscosity. So here, the very weak solution, if you compare to the pseudo-weak solution, this solution, we don't require it to satisfy the local energy inequality, and we don't even require it in the following Sobolev space. So it's a much weaker notion of solution. But thanks to the second condition, at least this solution will have uniformly bounded finite kinetic energy. And the most interesting solution to that we can apply this theorem would be the constructed non-conservative weak solution for the Onsager conjecture. So from this solution, we can say that, well, we can at least write the constructed solution as vanishing viscosity limit of some very weak solution, which has a finite kinetic energy. So this we can say. And another way of relaxation would be the following. So this approach is more related to when we try to obtain the negative answer. So it's so the approach is the following. So first we investigate the solution, which can be written as a vanishing viscosity limit of pseudo-weak solution to the Navier-Stokes equation. So we investigate what kind of property such solution to satisfy, and see if the constructed solution to satisfy such property. And if not, of course, it can't be written as a vanishing viscosity limit of this sequence. So in this direction, Duchon and Robert proved the following. If an Euler flow can be recovered as a vanishing viscosity limit of pseudo-weak solution to the Navier-Stokes equation in L3 topology, then such flow always satisfies the local energy inequality. So similar to the Navier-Stokes equation case, the local energy inequality means that we don't allow the creation of kinetic energy from the irregularity of the solution. So in every local region, the kinetic energy will be either conserved or essentially dissipate. So now the question is whether the constructed solution for the Onsager conjecture satisfies the local energy inequality. Of course, the solution that Isett constructed has the creation of kinetic energy in some region, so it wouldn't satisfy local energy inequality. And if you also consider the solution which has the non-increasing energy profile, but those solution is difficult to say whether it satisfies the local energy inequality or not. So that leads to a strong Onsager conjecture, which you can consider it as a combination of original Onsager conjecture with the local energy inequality. So the statement of the conjecture is the following. For any alpha less than 1/3, we can construct alpha Hölder continuous weak solution to the Euler equation, which not only satisfies total kinetic energy dissipation, as in the original Onsager conjecture, and also it satisfies the local energy inequality. So compared to the original Onsager conjecture, the original one is only about total kinetic energy, so we don't know what's going on our kinetic energy in every local region. But on the other hand, in a stronger version, since it satisfies the local energy inequality, in every local region, we know the kinetic energy will be either conserved or dissipated. So that's one of the big difference. And another remark is that you may wonder, what about the conservative part? As I mentioned earlier, Duchon and Robert already proved that when alpha is greater than 1/3, the solution will satisfy local energy equality. So the positive part, the conservative part is already known, so I didn't state it here. So let's see some non-results related to this conjecture. This bounded weak solution which satisfy these two conditions are first constructed by Lellis and Giri. And a couple of years ago, Isett constructed that Hölder continuous solution for alpha less than 1/15, which satisfy this property. And the range of alpha has been improved by Lellis and myself recently. And one remark is that, in fact, the constructed Hölder continuous solution satisfy the local energy inequality strictly. So the constructed solution actually have the kinetic energy dissipation in every local region. Okay. So far, I've introduced a strong Onsager conjecture. Do you have any question? If not, let me move on to the uniqueness and non-uniqueness problems. So the motivation of this problem is again goes back to the main question. We said that are the constructed solutions physically acceptable? Indeed, another way of showing some given solution is a physically acceptable would be by obtaining the uniqueness of the solutions. So that's the motivation. And let's first consider the Burger's equation, which is a 1D toy model of the 3D Euler equation. So here's the equations. And now the velocity is given, is defined on a one-dimensional spatial domain. And thanks to the simplicity of this spatial domain, we have better understanding on its solution behavior. So for example, when the smooth initial data is given, we know that it can develop singularity in finite time. So more precisely, it can develop some discontinuity in finite time. And the solution which has such jump discontinuity, which is also called shock solution, are pretty common. So the people has been investigated bounded weak solution, which is a solution class which is a solution class including such shock solutions. Okay. But the problem is this bounded weak solution, we can't guarantee the uniqueness all the time. This means that even though you start from some bounded initial data, you can have two different bounded weak solution emanating from the same initial data. And as an explicit example, we have the following. So let's say the initial data is given as the following. So when x is positive, it has the value 1. And when x is negative, it has value -1. And from this initial data, we know that the stationary solution can be a solution. So as time goes by, it doesn't change its solution. It doesn't change the value. And another solution, another possible solution would be the following. The solution that these two constant states are heading to the infinity. So the graph of the another solution will look like this. So this is value 1 and this is value -1. And the graph in between will be described by x over t. So as time goes by, this constant state goes to the infinity. Then you may ask, so which one is the physical solution? So which one really, which one is the solution that you really see in the real world? So for that, people impose the additional admissible condition, which looks pretty similar to the local energy inequality. And it turns out that under this condition, we can single out a unique solution. So if you look at the previous example, the second solution actually satisfies the inequality, while first equation is not. So you can see that the actual physical solution would have the following profile. Okay, then the question is, does this successful story of recovering uniqueness extends to the general system, hyperbolic system of conservation? So let's first go back to the 3D incompressible Euler equations. From Isett's result, we already have the non-uniqueness of weak solution in C alpha space for alpha less than 1/3. Indeed, Isett constructed a solution which starts from 0 initial data, but it's non-trivial. But on the other hand, if you start from 0 initial data, we also have 0 solution as a trivial solution. So apparently, we have 2 solutions starting from 0 initial data. And to find which one is the physical solution, as we did before, we can impose the additional local energy inequality to the solution and see if we can recover the uniqueness. So here, the admissible weak solution means that the weak solution which satisfies the local energy inequality, but it turns out that in this 3D case, the uniqueness, we can't recover the uniqueness. So we know the non-uniqueness of the admissible weak solutions. So the result actually comes from slight modification of the proof of the partial result for the strong Onsager conjecture. So the first result was obtained by Lellis and Giri, and the best available result is the non-uniqueness of this admissible weak solution in C alpha space for alpha less than 1/7. And moreover, even though U requires the solution to satisfy local energy equality instead of inequality, the such solution is still remains non-unique. So even under more, even though we give a slightly more restriction, we still have non-uniqueness. Okay, and let's consider one more system, which is called isentropic compressible Euler equations. So as you see from the name, this equation describes the motion of compressible fluid. So the density appear as a new unknown function in the system. And these systems are, as in the incompressible case, again derived from the mass conservation and momentum conservation. But different from the incompressible case, the pressure is no longer a known function, rather it is given as a function of density. And a typical pressure rho would be given as follows. This rho is actually for the polytropic gas. Okay, so we again ask the same question. Under some suitable admissible condition, can we get the uniqueness of a bounded weak solution to this equation? So first, we need to find a suitable admissible conditions. And a natural candidate comes from the entropy inequalities. But the only available entropy inequality for 3D isentropic compressible Euler equation is given as follows. So if you look at it, this inequality describes the dynamics of total energy, which consists of the kinetic energy and specific energy, which is determined by the following relation. So it says that the total energy is either conserved in every local region, or we allow some extra dissipation. So then the question is, for bounded weak solutions, can this admissible condition serve as the selection principle? It turns out that the answer is no. So Lellis and Cyclidi proved the following theorem. So it says that they can find bounded initial data where the initial density is away from vacuum, for which they can find infinitely many bounded admissible solutions. And the result holds n-dimensional space for n greater than or equal to 2. And after that, Schodroli, Lellis, and Camillo proved that they can actually make the bounded initial data, which generate infinitely many solutions, to have specific form, like the form of Riemann initial data. So the Riemann initial data is the one which consists of two constant states. And they show that they can find a Riemann initial data which generates infinitely many bounded admissible solutions, but the result is restricted to the 2D isentropic compressible Euler equation, which has a specific pressure law. So the benefit of having such initial data would be the following. As a corollary, they can construct Lipschitz initial data. So since the initial data is Lipschitz, the solution can be continued uniquely for finite time. But after that time, it can develop the following form of singularity, so discontinuity, and then we can have the non-uniqueness. And there are several some extension of this result or improvement of this result. But the point that I want to make is that all previously constructed solution contains the discontinuity. Then I was wondering, is the discontinuity a source of the non-uniqueness? In other words, what if we consider a continuous weak solution? Then can the admissible condition serve as the selection principle? But the answer again turns out to be no. And this is my research result with Vikram Giri. And the theorem states the following. So for any alpha less than 1/7 and any initial density, any smooth initial density away from the cube, we can construct the infinitely many admissible weak solution emanating from same initial data. And if you look at the constructed solution, the density remains smooth in space-time, but the momentum has a C alpha regularity for given alpha. And the result holds for general pressure law, as long as the pressure is a smooth, given as a smooth function on the range of the density. And furthermore, as you see in the incompressible case, even though we require the solution to satisfy this local energy equality, the constructed solution still, we still have the non-uniqueness result. Okay, so this is the, that's all I prepared, and thank you very much for your attention.
Let's thank the speaker for this wonderful talk. So I open the floor for questions.
So I have a couple of questions. So thank you, Hyunju, for this beautiful talk. Although you did not present any technical result, but I have a technical question. May I ask you a technical?
Yeah, sure.
So I was wondering, how are you doing this gluing step, for example?
You mean gluing in the sense of the Isett?
Yeah. So are you following the same strategy, or you are
No.
allowing the Mikados to interact? The next generation Mikados to interact with the current generation.
So, okay. So the main reason, sorry for the others, I guess I need to talk like in a technical term, but so the main reason that Isett used this gluing argument is to deal with this interaction between the transported Mikado flow from the consecutive time slot. So that's the main reason that that he used the gluing technique. But with local energy inequality, it doesn't seem to be. It doesn't. It seems that it's pretty difficult to apply the gluing argument. So we sort of make a detour. Instead of using this gluing argument, we sort of place the pipe carefully so that we avoid the interaction.
So you still have enough place to actually put the next generation Mikado to that current generation.
Yes. So the main observation is something like this. So the transported Mikado flow, if you just proceed this short time of the scale, like gradient of UQ inverse, 0 inverse, still the pipe can be distorted a lot. But if you restrict in a small region, the pipes still remain as a just thin pipe. So based on this observation, we also put the space discretization. Then each cell, the transported Mikado flows still remains almost thin pipes. Then by using some combinatorial argument, you can carefully put them to have to avoid all the interaction. But of course, to improve the regularity further, you need something like a gluing argument. But we first want to check whether this Mikado flows works well with this local energy inequality, because in the previous work of Isett, he used this just a plain wave. I guess the main reason is he doesn't know how to apply the gluing technique.
Okay, so cutoff in your case in space-time, right? Not only time?
Yes. It's also space-time.
Right.
Yeah, and
No, please go ahead.
Yeah, so if you actually apply the same idea for just to prove Onsager conjecture, it sort of gives this a new proof of Onsager conjecture, but the range of alpha is restricted to 1/5.
Okay.
Just
Yeah, I had another nice question. So far, all this convex integration method, you are explicitly using the fact that your flux has like a quadratic structure, or in your case, like a cubic structure. So what can you say about a general flux? For example, if I give you a Lipschitz flux, per se, can we do something about that without knowing a precise structure?
sorry, if you give what
Any general, let's say, Lipschitz continuous flux.
continuous class?
I mean, you replace u square by, let's say, f of u, where f is a Lipschitz continuous.
Mm-hmm.
Is it possible to do something
So
along
you
this
mean
way?
for the really general equation, can we apply this convex integration scheme? Is that the
Yeah,
question?
yeah. In other words, how do you actually cancel this Reynolds trace for a general function? Is it possible?
So I guess for the general one, I guess just more. I guess the original convex integration scheme is more used, because I feel like that scheme is applicable for more broad equations. But Nash's idea, I'm not sure. It really depends on the equation. And yeah, I mean, so far we haven't had a really general way of I mean, we haven't had a proof for how to apply for general equations.
Okay, thank you.
Yes, but maybe the way I usually check is just play with the plane waves first. And if that works, just try to, I mean, just see if how to improve the regularity and so on. But yeah, just usually I play with the plane waves first to see whether you can make the scheme work or not.
Okay, thank you.
Are there other questions from the audience? So there was one from, I think, Shyam, and the other from Arpit. So Shyam, do you have a question?
Yes. Hello. First of all, thank you very much for the talk.
Thank you.
So I have one question from the compressible case. So what would be a good conjecture in your opinion for uniqueness?
The conjecture, I guess, is still like, roughly speaking, when alpha is 1 would be the conjecture. But as far as I know, there are some relaxation of this condition. Like, for example, only one component needs to be ellipsis, or like something like that. I don't know too much details, but I guess still the conjecture can be 1. But I mean, even in the incompressible case, I don't think with the convex integration scheme, I mean, just what we know, we can reach 1. I guess 1/3 is really the critical number.
Okay, so just to inform you, we have a result which is for alpha greater or equal to 1, half, which is slightly better than weak strong uniqueness.
So you are talking about weak strong uniqueness.
No, I'm saying that, let's say if you have let's say C alpha solution with alpha greater than half with the velocity condition on the gradient, which is again weak, one-sided Lipschitz, then you can have no other weak solutions.
So you mean one component has a Lipschitz?
No, nobody is Lipschitz here. One component velocity is one-sided Lipschitz. It's like only condition.
What do you mean by one-side Lipschitz?
So the Lipschitz norm can blow up, but it should have the gradient as a non-positive definite matrix.
Okay.
So that's what I mean.
I see.
But what we could not prove anything about the optimality. So I was wondering what would be a conjecture. What would be the critical alpha, let's say?
Well, yeah, I don't know. Yeah. I mean, for example, the analogous Onsager conjecture for the compressible equation, the alpha equal to 1/3 is the conjecture, and it actually proved in some sense.
Yes.
But
And also, let's say if your
non-uniqueness.
solution is continuous intersection BV for the compressible, then also it is equality. At least from this positive point of view.
Yes.
So I was really asking the question from the uniqueness point of view, what is the good conjecture to ask at this point? What would be the, let's say you have done the result for alpha less than 1/7, right? So do you think that it can be improved, or it can go to?
I guess if it's improved by the convex integration scheme, I guess the best alpha would be still 1/3.
Okay.
But that doesn't mean the 1/3 is the critical one. Just what I'm saying is just if you use convex integration scheme, I guess that's the best alpha that you can achieve.
Okay. But from the positive point of view, what would be your conclusion, let's say, or a conjecture? Get the real uniqueness result.
You just said that alpha equal to 1 is maybe not the right number.
Yeah.
I mean, yeah, so I'm not perfectly sure from the positive point of view. Well, I haven't, I mean, in that direction, I haven't done much research. So I guess you have better intuition than I have.
All right. Thank you very much again. Yes.
Thank you for the good question.
Arpit, you can unmute yourself and go ahead.
So my question was about the physical admissibility of the solution. Like I have just seen in the literature, some paper of Buckmaster and Recall that even Navier-Stokes equation has non-uniqueness issues. So to call a solution of Euler equations admissible as being limit of solutions to Navier-Stokes equation when viscosity tends to 0, don't we first require the uniqueness issue to be sorted for Navier-Stokes?
So yes, but like what they proved was the non-uniqueness of very weak solution. So it's sort of similar to this result, but what they show is the non-uniqueness of this pretty weak concept of solution. But I guess we consider more physical solution as the solution which satisfy all these conditions. So still there's hope that this suitable weak solution can be I mean, as long as you can write it as a vanishing viscosity limit of pseudo weak solution, you can still discuss the questions. Because I mean, like pseudo weak solution, I mean, it doesn't have much singularity. The singularity is pretty little. So, well, it's not proved whether this solution is really unique or not, but I guess we sort of have some belief that still the problem is reasonable. Okay.
Yes, that makes sense. Thank you very much.
Thank you.
Are there other questions from the audience? Okay. In this case, let's thank the speaker again. recording.